Hi, guys. This is Miss Segura. Today we are finishing up stoichiometry, so you should have just finished your exam, and we're going to be talking about gas laws. So hopefully, you guys will feel a lot more comfortable doing the gas laws. Much easier, in my opinion, than what we just covered stoichiometry. So, this is the handout that you should have received. And first thing it asks you to do is let's read the background. In this investigation, you will examine three gas laws, including Boyle's Law, Charles' Law, and Gay Lussac's Law. You will explore how manipulating the variable of volume, which is represented by L for liters, pressure, represented by ATM for atmospheres, and temperature, represented by K for Kelvin, can affect a sample of gas. The formula of each of the gas laws, these are three of the six that we're going to be learning about. So the first one is Boyle's Law, where an initial pressure and volume equals a final pressure and a final volume. Charles' Law, where volume 1 divided by temperature 1 is equal to final volume 2. That's what the 2 means, divided by final temperature. And then Gay Lussac's law is involving pressure initial divided by temperature initial, which equals pressure final followed divided by temperature final. So the first thing you're going to do is see if you can solve for x, because if you'll notice, this one is very closely related to Boyle's law. It's just a linear equation. This one is closely related to Charles' law and Gay-Lussac's law, and this one is also representative of Charles' law and Gay-Lussac's law. So you're always going to be solving for x in these problems. So it's just reading the problem, figuring out what you're solving for. But I really do like this lesson and the simulation because it does allow you to see the particle arrangement, which for me, I'm a visual person. So, how would you solve for x in A? So, if you can remember from algebra, you need to isolate x. So, in order to do that, if I want to get x by itself, I need to undo this operation here. And that is multiplication. So, the reverse of multiplying is dividing. So, what I would do to this side, I would also have to do to this side. So, I would divide both sides by 1.76. And then this 1.76 divided by 1.76, that divides out and that allows me to isolate x. So now on the right side, all I have is x, and that's equal to this new formula where 1.34 times 5.46 is divided by 1.76. And this is how you learn it in algebra. These numbers don't really mean anything. It's just solving for x. But in this lesson, you're actually going to be solving for um, an unknown pressure, an unknown volume, and an unknown temperature. So x means something now. So you're just applying your skills of algebra to something more meaningful. Okay, so if I take 1.34 and I multiply it by 5.46, when they're in parentheses like that, it just means you're multiplying. I like to hit equals here, and I'm going to divide it by 1.76. And that is how we get x. So I would round this to 3 digits. So I would round it to 4.16. So this 5 is going to round up to 6 because that 7 is 5 or more. So we add one more. So 4.15. And now there are no units associated with these three problems here. It's just solving for x, like what you would do in algebra. But when you do the actual formulas, you're going to have to put a unit. associated with it. All right, so let's look at B. How would I solve for x looking at an equation like this? Now, there's a couple of different ways that you could approach this. You could cross multiply and then cross multiply these two and these two. You end up dividing by this number here, or you could multiply both sides by the reciprocal of 1 over 267, which would be 267 over 1. I think most of y'all are comfortable with cross multiplying. So if I cross multiply these two, I'm going to get x times 332. So I just cross multiplied those, right? And then I'm going to set that equal to this set of numbers that I'm also cross multiplying, which is 4.38 times 267. And now it looks really closely to this equation that we had here. Okay, so I've just cross multiplied. And some of y'all might be like, why is she writing it out? Why doesn't she just multiply these two and divide by this? Well, this is what you're doing when you just cross multiply and divide. You're setting up a new equation. Okay, so if I want to isolate x, again, I have to undo this multiplication here. And I do that by dividing. So I'm going to divide this side by what is being multiplied by x, 332. And as you can remember in algebra, whatever you do to one side, you're going to have to do to the other side. So I'm going to divide both sides by 332. This divides out, and that will equal 1 times x, which is just x. And then now I'm going to calculate. So 4.38 times 267, and then I'm going to divide that by 332. And I get 3.52 rounded. The 2 stays the same, 3.52. So that is B. All right, so this could be a Boyle's Law equation, and then this could be like a Charles or Gay-Lussac equation because they're set up like this one's set up like these two, and this one is set up like this one. Okay. All right. So letter C, how would you solve for this? Well, you could move x over. So you can multiply both sides by x, and then you would have 2.25x divided by 295. Trying to think about that. Or you could just cross multiply. So I would just cross multiply these two. Same way I did this. Now I cross multiply 2.25 times x. And I'm going to set that equal to the other set of numbers that I'm cross multiplying, 4.85 times 295. Okay. Again, I'm going to solve for x by isolating it. So I'm going to undo this problem by dividing 2.25. Divide this side by 2.25 also. This reduces to x and then my new equation. So 4.85 times 295. And then that gets divided by 2.25. And I get 635.8. Round that to 3 digits. That ends up being 636. Okay? All right. So we have just done 3 examples of potential problems that you'll be seeing with these 3 gas laws here. Okay. Now on number 2, it says, briefly describe in your own words the meaning of each of the following variables. So things that can change. volume can change, the amount of space a gas occupies can change, pressure can change, and temperature can change, as you'll see in the simulation that we're going to be using for this. Is that an airplane? Okay. All right. So, guys, I want you to describe in your own words. If you Google it, fine. Don't write down what Google says. Okay. Write down what you translate Google to be saying in your own language. Okay. But it says here also write down the common units of measurement associated with each. So, first, you need to write down your definition, and then you need to look for common units of measurement. Okay. So, I'm going to do the units with you because if you Google these, you're going to be finding so many units that really don't pertain to what we're doing here. Okay. So, units of volume is usually going to be measured in liters, like what we saw in stoichiometry, liters of a gas, the amount of space that it occupies, or milliliters. Okay, if it's a smaller amount, this is like usually for larger amounts, and this would be like smaller amounts. And this could be for gases or liquids. The units of pressure are going to be represented by the most common one that we're going to see in our lessons is ATM, which represents atmospheres of pressure. So, all the gases that exist surrounding you right now, all those gases from sea level up until space, that would be considered one atmosphere of pressure. There's also other ones. There is PSI, pounds per square inch. So if you've ever checked your tire pressure, you're going to use pounds per square inch. There's another one called kilopascals, and there's another one called torr. And then if you ever open up your weather app on your iPhone, you'll notice that if you look at the pressure, it's in inches mercury, but in metric system, we measure it in millimeters of mercury. And that has to do with a barometer and the way a barometer is built. And if you have questions about that, guys, feel free to Google a barometer. You might hear the weatherman saying the barometric pressure, blah, blah, blah. Okay. Temperature, there are units that you're familiar with. You guys are used to degrees Fahrenheit, right? That's how we look at when we look at our weather app and it says 65 degrees, it's in Fahrenheit. In science and in the metric system, we commonly use degrees Celsius, or we will use the Kelvin scale. Okay? And feel free to Google the Kelvin scale. It's spelled like this, Kelvin. Now, this is the unit that we really want to focus on in chemistry, in gas laws. It's the absolute zero scale. So feel free to learn more about that on your own. Okay. All right. So let's go to the next page. So the next page is having you visit this website. The website is going to be on Canvas. Okay. So if you click on this website, it will be on Canvas and it's going to take you to here. Okay. So you see some options here. You see Boyle's Law, you see Charles' Law, and you see Gay-Lussac's Law. I'm going to refresh it because these particles should be moving. All right, so make sure that you select the Boyle's Law tab to begin. I have Boyle's Law tab selected, and it will be shown in white. You should see the picture below on your screen. That's exactly what I'm seeing on my screen. Now, these little red particles are representing particles of a gas. And so what we're going to do is we're going to observe the behavior of these gases as we adjust different variables that we discussed before: volume, pressure, temperature. Okay. So it says, which one of the three variables, I'm reading on my paper here, which one of the three variables, pressure, volume, or temperature, cannot be changed in Boyle's law? This variable is considered a constant. Okay, that means that in order for us to see or observe what happens in Boyle's law, um, one of these, pressure, volume, or temperature, must remain the same. Okay, throughout. All right, so let's see. Are we able to adjust volume? Yes. Look at that. The amount of space that this gas is occupying is the space is able, we can adjust it. Okay, so I can manipulate this one. So I can change pressure. Okay, so if I raise it or lower it, something you'll notice is happening to the volume. Some type of relationship is going on. As I raise the pressure, look what's happening to the amount of space. As I lower the pressure, look what's happening at the amount of space. Now, the one that I can't change here, guys, I can't change the temperature. Okay, so on number one, which one of the three variables is considered constant? You're going to write down temperature. Temperature remains constant. Okay, so we were able to change pressure and volume. And if you look at Boyle's law, you'll notice that Boyle's law does contain pressure and volume as variables. Okay, let's see what it says next. Using the volume control arrows, reduce the volume of the gas to 1.70 liters. Okay, I'm reading number 2. So I'm going to reduce the volume of the gas to 1.70 liters. I hope you're doing this with me, because click reset so that everything is reset. Because if you're just watching me do it and not doing this on your own, it's going to be much more difficult to do. You guys are going to end up doing Charles' law and Gay-Lussac's law on your own. So make sure that you're pausing the video if you need to do this with me. So we're going to reduce the volume of the gas to 1.70. Okay, so notice as I reduce the volume, we're looking at V2. Okay, I want that to go down to 1.70. And there it is, 1.70. In the space below, record your observations regarding the behavior of the particles in the gas sample as the volume is reduced. Make certain to discuss collisions in your comments. What is a collision? Have you ever heard of a vehicle collision? Usually that involves one or two vehicles or more colliding, crashing into each other. So we're looking at how the particles are bumping into each other, basically. So I'm going to reset it so you can see how they behave before I change that volume. So notice how frequently they're bumping into each other. Okay. Now, when I reduce the volume to 1.70, oops, I don't know about you, because that space has been reduced, I'm noticing there are more collisions happening. And it makes sense. The, less space you have in a room and the more people you have in there, the more opportunity there is for them to bump into each other. Okay? So I'm going to write that down in my observations. Where is it? Right here. So I noticed the particles were bumping into each other more. As the volume was reduced. And then you could put in parentheses, we saw more collisions. Okay? All right. Calculate the new pressure value for the gas, showing all of your work. Check your final answer for part B by clicking the calculate button next to P2. Okay, so we need to calculate the new pressure using this formula. Okay, so if you'll notice on the simulation, P2 is covered. Don't uncover it. Don't click that yet. We'll click it in just a minute. So we're going to plug in. Remember, temperature remains constant, so temperature is not a factor in this problem. So I'm going to plug in P1 with 1 atmosphere and V1 with 3 liters. Okay, so I'm going to do that right here. P1 is 1 atmosphere. V1 is 3 liters. And I'm going to set that equal to, guys, P2 is my X, but I'm going to call it P2. You can write X if you want. This is our X. And then our V2 is what we see here. Our new volume, we've reduced it, is 1.70 liters. Okay? All right, so how did we solve this before? So if you look at this equation here, this is what I have written down so far, guys. 1 ATM for P1, 3 liters for V1, P2 is our unknown, and 1.70 is our new volume that we reduced it to. So if you'll look at this paper here, it looks kind of like this, right? So the first thing that we have to do is isolate X and then set up a new equation that represents X. Okay, so we're going to do P2 is our X. So I'm going to undo this right here. It's being multiplied, so I'm going to divide. So 1.70 liters on both sides. Okay, I'm going to divide this out, and it's going to equal this new equation. Now, we need to make sure that we can divide out whatever units that are being divided out. This times this is being divided by this. Liters divided by liters, if you'll remember, when we did stoichiometry, it divides out, it reduces to 1. Okay? So in the calculator, you can calculate using this equation here. I don't know about you, but 1 times 3 is 3, but you can enter that if you want. 1 times 3 equals 3, and I'm going to divide that by 1.70. Oops. And then equals, so my new pressure is 1.76. And you'll notice that the new pressure unit is the one that's left over here, ATM. So I have a pressure of 1.76 ATM. All right.